Okay, for our last screen demo, we're going to review how to use SEM within the R environment. So you can see down here, I've already loaded up the package that we're going to be using, KernLab, and made it a library, and also defined the variable where data file that we're going to play with. It's actually bank data. Let me actually just, now that we have the file, it's a CSV file. So I'm going to read in that file. So we'll call it bank data. We're going to do read.csv. We'll do data file. The separator is quote, or semicolon, sorry, and there is a header. You can see we read it in. Let's take a look at the structure of it. Okay, so we read in a data frame because it was a, CSV, and it has 4,500 observations of 17 variables. And it's bank data, as I said. And we're trying to understand or predict why, which is, does the loan kind of default get paid back or not? Maybe get paid back is the easiest way to think about it. And so really it's yes or no, and that's trying to predict. We have a whole bunch of different attributes. This kind of describes the person and some information about the loan, for example. So the age of the person, the type of job, you can see there's 12 different types of jobs. If they're married or not, you can see there's 3 levels. Divorced, married, and my guess is the third one's probably going to be single, and a whole bunch of different other attributes. We can take a look at the attributes a little bit. Do a summary of bank data. Again, so you can see kind of this distribution of age, the types of jobs, the breakdown of the marital situation, education, primary, secondary, and tertiary, right? So then have they previously defaulted, information about their loan balance, a whole bunch of different other things. Previously how they've done, and then in the end we want to predict why, which again, yes, were they able to pay or not? And the yes is bad in this case, and the no was it wasn't an issue. So we can see there was, again, this number. So now, what do we want to try to do? Well, let's kind of first do, I guess, test and train data. So the first thing we have to do is nrows, figure out how many there are. We kind of saw that, but it's probably better just to do it in a calculation. Right, we saw that previously, right? So if we would have done up here, right, 45, 21 observations, that's how many we have. So now that we have that, maybe my question is, where should the cut point be? How many should be test data and how much should be trained data? What do you think, based on the fact that we have 45, 21? Well, it should be close to 3,000 because we want 2/3, but we can do it kind of more programmatically. So we'll say the cut point. We're using the floor function just to round it. And there it is. That's 2/3 of the way through. Now we want to kind of, again, if you remember from before, we want to randomly create or kind of distribute what's test and what's training. We don't want all the first 2/3 to be training, the last 1/3 to be test, because the data could be sorted in some way that we're not aware of. So the first thing we'll do is we'll create random indices. And we do that by using our sample function that we've used many times before. If you're not sure exactly what that looks like, see, these are just different indices in the range of the full spectrum. So it would be up to 45, 21. But now we have a list of those indices. And we can create the test and train database on this. So we have bank data dot train could be that. We can have cut point. And something similar for test. rather than starting at the beginning, we want to do cut point plus 1. Probably need some parentheses to make sure we don't mess that up. Then we're going to go to the end. Let's take a look at what we just created there. Same factors, everything, but it's 3,000 for the train. And test b.train. So that means we messed up because the data frame is there. So let's take a look at what we created here. I see my parentheses in the wrong spot. Let's try it this way. There we go. See, 1,500. So 2/3 are training, 1/3 is test. You saw previously I had a typo of where I put my parentheses, and that's why as you kind of keep going through this, even though now we're pretty expert, and obviously I knew what I was doing, I made a stupid mistake, and that's something you want to kind of look at as you kind of go through this R coding yourself, just to make sure you don't do anything kind of silly mistakes, or I would call them stupid mistakes that I just did. So now let's actually try to build a model. So let's say model. Use the KSVM. Again, we're trying to predict Y. Let's start with everything, which is the dot. And then the data equals bankdata.train. And we've built a model. And now we want to do with the model, we can take a look at the model, but what we want to do with the model is use it to predict the test data. So first we can take a look at the model. We can see, for example, in this model, that the training error was around 8%, which is really good. It means it's about 92% accurate on the test that we did at training. But now we want to compare that to actually how it works with data it hasn't seen before. So the way we do that is we're going to ask it to predict based on the model we built, and then the data that we actually want to test. So now we have a bunch of predictions. And what we can do is we can kind of take a look at this table. Okay, so what we have is what we predicted, diagonals is accurate, and kind of this cross diagonal is not. So when we predicted no and there was no, that was 1,300 of them. When we predicted no and it was yes, was 134. And when we predicted yes, but it was no, was 21. We predicted yes and it was yes, was 31. So my question is, based on this, what percentage do you think is correct? How did we do? Well, let's take a look and do it programmatically. So the total correct. Well, let's store the results maybe first. So rather than just print it out, we'll store the results. Again, we can kind of do this, right? And now we can say the total correct equals the diagonal again. So it's 1, 1 plus 2, 2. That's how many we have correct. And the total itself was the number of rows. Oops, number total in test. Again, that makes sense. So now we can actually see so it's about 89 or 90% accurate. So that's pretty close to what it was in the training. If you remember with the training one, it was around 92%, and now we're around 90, so we really didn't decrease that much. So that's actually a pretty good sign. And now maybe the question we'll have is, Let's try to build another model. I'll go back and get the model. Call it model 1. And rather than everything, let's have it be just, I don't know, education. Is education a good predictor of if somebody's going to be on time on their loan or not? What do you think about that? Let's explore the model. First thing we can do is we can take a look at the output of the model. Training error is a little higher, but not much. That's actually a pretty good sign. So this would mean it's about, we had about 11% error. Remember before it was 0.08, 8% error, so it's pretty close. And our training data was kind of in the same ballpark. So far it looks pretty good. But let's see how it does when it tries to actually predict. We're going to predict model.1, so this is the new model. And again, we want to do the test data. And we can kind of go back and do the results. It'll be the exact same code just to show you that. We'll actually get the results that way. Okay, so we store the results. And we can go back and actually get the number total correct. Total and test. And again, so total correct divided by total and test, 89, so that's almost exactly the same. Wow, this looks good. Do you really think we did that well with just the one attribute being the education? What do you think about that? Well, we can't just look at this. We actually take a look at the actual matrix of kind of what's accurate, what's been predicted. And that's when you can see that we got a problem here. Well, the percent correct is good. Basically, you can see the model basically just said, always say no. So it's actually, it's decided it can't figure anything out, and it knows that the easiest way just to do things based on the percentage of times that there's an issue is so small, it just makes sense to always say yes. And I think kind of the thing you want to take away from this is that while looking at kind of the percentage correct and kind of the accuracy of the model is helpful, you need to kind of take a step back and just conceptually look at what the model is predicting, and does that give you a comfort level about how the model is working or not. So I think with that we'll stop.